I'm going to work the entire practice exam 3 with you here. So I know many of these you will already know how to do, but I want to make sure that everybody is okay with each one of them. So I'm going to be working through all of these with you. And um, so I'll just go ahead and start with number 1 and go from there. Okay. Got to get my screen set up so that everything is okay. Okay, well, I've lost this one. Okay. Now, what you should see on your screen is you see a big copy of the question on practice exam 3 and a little small, right now you're seeing a little small thumbnail that has my work area on it. I'll be switching back and forth between these two to give you more focus on the solution after we start working with the problem. So this first one is we want the bond angle in that has a 120-degree angle. So we want to find a molecule that has this bond angle in it. And we have some choices. A is ClF3. B is SB. Br6 minus. And C is PCl4 minus. And D is BeCl2. So now let's go ahead and start working through the ones to do this. Now we need to do this, we need the VSEPR notation. And the way you do that is we need the number of valence electrons. So let's start with A. We've got a chlorine that's in group 7. There's 7 valence electrons for chlorine. And of course, you can get that from the periodic chart by getting just the column. So if I'm in chlorine, it's in group 7A. So it has 7 electrons. I've also got 3 fluorines, and fluorine is also in group 7. So it's got 7 as well. So this is going to give me a total of 28 electrons. Now to get the shape of this molecule, we're going to do the math method. You take 28, and we're going to divide by 8. When we divide by 8, we'll get a 3 here, and that's 24. The remainder is 4. We take the remainder, 4, divide that by 2, and we get 2. So this molecule is an AX3E2 type molecule. So to get its shape, we've got 3 things bonded together. So 3 atoms bonded and 2 lone pairs, that's 5. The shape of an object that has 5 pairs on it is trigonal bipyramid. Now we have to account for where the electrons go first. And of course, the chlorine is going to be the central atom. It's going to be in here. And we have to put in 2 pairs of electrons. electrons have to be as far in angle as they can be away from anything else. So if I put, that would be in the equatorial plane, because in this plane the angle is 120, but you see from here down to the next atom is only 90 degrees from the axial positions to the equatorial positions. So the first lone pair goes in the equatorial plane. That's there, let's say. And then we're going to put in the next lone pair, which has to get as far away from this one as possible. So it goes in another equatorial position because the angle here between the lone pairs, not the bond angle, is 120 degrees. And now, if I put the 3 fluorines on like this, now my bond angles are 90 degrees and 180. From here around to here would be 180. So this molecule does not have a 120 degree angle in it, so I can eliminate A. If I'm doing antimony hexabromide, so let's go down over here and I'll do B here. To do that one, antimony is right here on the periodic chart. That's in group 5. So antimony has 5 valence electrons from the antimony, and bromine, there's 6 of them, so it's 6. And then bromine is also in group 7. Right there it is in group 7. So it's got 7 valence electrons times 7. And then this carries a charge. So I'm going to add one more to it. 6 times 7 would be 42, plus one more would be 43, and 5 would be 48. So I've got 48 electrons. Again, do the math on it. 8 divided into 48 is 6, and that's 48, and remainder 0. So this molecule is AX6. Well, I already know that it couldn't be this one, but let's go ahead and write it out. There is the shape of everything with 6 valence electrons. It has no 6 pairs of electrons on the central atom. So I can put antimony in here as the central atom, and then all 6 of these other positions are going to be bromine. Okay, and there's only 2 kinds of angles. There's 180 degree angle, and then all the other angles, say here to here, that's 90 degrees. All of them are 90 and 180. There is no 120, so it's not B. Let's do C. And if we do C, we get PCl4, and it also is negative. So again, getting the valence electrons, phosphorus is in group 5. It's right there in group 5. So it has 5 valence electrons. We've got 4 chlorines, and again, we've already seen chlorine is in group 7. So that, plus it's negatively charged, so we're going to add one more. So 4 times 7 will be 28, 29, 34. So we've got 34 electrons to go into this one. Let's do the math. You take 34, you divide by 8, you get 4, that's 32. And then remainder 2, you take the remainder and divide by 2, you get a 1. So it's an AX4E type structure. Again, 4 plus 1 is 5. It's going to be trigonal bipyramid like we saw up there. So we're going to get this kind of structure. Now, we've got one lone pair to go in. The lone pair has to go in the equatorial plane. I'll put it there. It could be in any one of those positions. Phosphorus is going to go here. Now, the chlorines go in the other positions. Like that. Now, again, we have 2 kinds of angles. Well, I guess we got a total of 3 angles. This one here is 180 degrees all the way around from chlorine to chlorine. this chlorine to this chlorine, this is 90-degree angle, but this one here is 120. So we do have a Cl PCl angle of 120. So this is the correct answer. Now, if we go to the last one, BeCl2, we can get it really quickly. We could do the math, but it really won't matter. Beryllium is in group 2, so it can only form 2 bonds. It can't do, I mean, I could do it with the math, but I don't need to because it can't have more than 8 electrons. It only had 2, so it can make but 2 bonds. So if I'm going to put the 2 chlorines here and the chlorine here, it won't be an octet rule molecule, but the angle is going to be 180. So it's not that one either. Okay, so that's the way, the full solution to problem number 1. Now, this video, by the way, is going to this video is going to take longer than an hour, so you can watch it in as you find time to watch it. Okay, so because hey Judy, I'm in the middle of a video. I'll have to call you back. Okay, bye. Okay. All right, so let's go on to number 2. I'm sorry for the interruption. That's my sister. She had a big birthday yesterday, and so I've been trying to get in touch with her to be sure she's okay and wish her a happy birthday. So she finally called back. Okay, now for number 2, let's go through it. Now, I need to go back to screen sharing in order for you to see what I'm seeing. But you've got a copy of it already. This is the practice exam 2, number 2. We want the hybridization. We want the hybridization in BrF3. Okay. So let's switch back to that then. And when we switch back over, now we'll do that by going here. And now you should be seeing a full screen picture of the question. It's the hybridization in BrF3. Well, the first thing we have to get, again, is valence electrons. The number of valence electrons, I've got bromine and fluorine, they're all in group 7. So I'm going to have 4 group 7 atoms. 4 times 7 is 28. Now let's do the math. 28 divided by 8 is 3. 24 with a remainder of 4. 4 divided by 2 is 2. So I've got 28 electrons, so it's an AX3 E2, and 3 plus 2 is equal to 5. So I have to use 5 orbitals to do that. In hybridizations, we have an s orbital. There are 1, 2, 3 p orbitals, and there are 5 d orbitals. 1, 2, 3, 4, 5 d. I have to do 5 of them. So I have to do this one, this one, this one, this one, and this one. So I've got 1 s orbital, 3 p orbitals, and 1 d orbital. So it's going to be sp3d is going to be the hybridization for it. And the 3 should be up here, sp3d. Okay, so that's the hybridization in this particular molecule. It's sp3d. All right, let's look at number 3 now. What is the molecular shape, not the electronic shape, of the same molecule? Now, here's what we have to be very, very careful about. We want to distinguish between the electronic shape and the shape of the molecule. We want the molecular shape here, not the electronic shape. So we've got 5 things to attach. So again, that's a trigonal bipyramid structure. And now we have 2 lone pairs to put in. So again, I'm going to put them here and here. They have to go in the equatorial plane. We did this earlier. And then I've got my bromine here and my fluorines in each of the other 3 positions. And we want the shape of the molecule if we ignore this part of the molecule where the lone pairs are. So if I just draw a structure like this, that's what we call a T-shaped molecule, kind of laying on its side. And the T-shaped molecule, let's get to see which answer that was. Number 3, the answer is C. That's answer C on the quiz. So we're good. Now, let's see, I need to start screen sharing, I guess. Yes, let's do sharing again. And now you can see the questions again and see the answer to this one was T-shape. Now let's go to, that was number 3. We're ready to now do number 4. And it says, how many unique resonance structures can be drawn for ONO+? ONO+ resonance. Okay, now let me switch it back so you can see a big copy of my pad. Okay, so this is the molecule we're trying to do, ONO+. Oxygen's in group 6, nitrogen's in group 5, and oxygen's in group 6. We've got 17 valence electrons. We're going to lose one. So that means we're going to have 16. If I take 16 and divide by 8, I get 2, 16, and none of this. And so I've got an AX2 type molecule. That's going to be linear. So I'm going to have an O, an N, and an O, like that. And of course, it's going to be a +1 ion, but I've got to put the valence electrons in. Now, here is an important thing. When I got that 0 right there, that means no lone pairs on nitrogen. So I do not want to draw any structure that has a lone pair on nitrogen. That means I've got to create the octet on nitrogen with multiple bonds. And I can do it this way, for example. Now, of course, that's +1. Now, I can double check. 2, 4, 6, 8, 10, 12, 14, 16. So that is the correct structure for 16 valence electrons. That's one of them. So that's one resonance structure. And there's no way to draw another one from that. But I can get 8. I can go back to my original structure that I had with just the sigma attaching bonds to the atoms like that. And another way I can get 8 on nitrogen is make one of these bonds a triple bond. Now, if I do that, I need one lone pair on oxygen. And essentially what we've done is we've moved a lone pair on this oxygen into here and a pair of electrons right there out to here to create this structure here. And if you recall, that's exactly what we meant by resonance structures. These structures are resonance structures I can get them by moving pairs of electrons from this one around to produce this one, or vice versa. If I wanted to go from that one, I'd move that pair in there and that one out there and get that structure. So these are resonance structures. So this is resonance structure number 2. It's not like that one. This one has 2 double bonds, and this one has a triple and a single. Now, you might think, well, okay, here's another resonance structure. Let's do this one. And indeed, that would be a resonance structure if I did it. I just moved that pair of electrons in and that pair of electrons out. It would be the same. But this one here is just this one here turned around. If I just take this one and flip it over, I get this one. So this is not a unique structure. This third structure is not unique. And that's the key word in answering this question. The question said, how many unique structures do we have? Not counting that one. And we're going to have 2 unique resonance structures. And if we go back to our view again to look at the question, you can see that how many unique structures, the correct answer is 2. And that's in C. Okay, moving right along. Now, we're going to number 5. And we want the resonance structures, 3D resonance structures for this molecule that's shown on here. And then we're going to answer some questions about it. So we've got the molecule is H2, C, C, H, C, N. Now, we want the VSEPR for the middle carbon atom. This is number 5. Now let's switch back so you can see my pad as I explain it to you. Okay, so this is the molecule. Now, this one is clearly not a central atom molecule. You can't use the math on this. What you have to do is think about the way each of these individual atoms can bond and what their bonding rules are. Hydrogen can only have one bond. So this structure couldn't be H attached to carbon. Both of these hydrogens have to be attached to that carbon. The carbon molecules have to have 4 bonds. Now there's lots of ways we can do it. We can have 4 single bonds like that. We could have, you could have 2 singles and a double. You could have 2 doubles, or you could have a single and a triple. So all of these are the ways, possible ways, that carbon can be bonded. And now nitrogen, the only other atom in this bunch, nitrogen is just got, it's got 1 lone pair always and 3 bonds. So it could be 1 lone pair and 3 single bonds, or I could have 1 lone pair and a double and a single, and I could have 1 lone pair and a triple. So those are the 3 ways nitrogen can bond. So let's go back and build these pieces then. So if I put the carbon here and the carbon here, that hydrogen can't be in the middle. So it has to be off to the side. I'm going to draw it next to that one, and that's the way the formulas usually are written. When I've got an atom in the middle of the molecule that can only bond in one place, it belongs to the atom in front of it. That's where it's going to go. And this carbon and this nitrogen. So I can put all of those bonds in. I can put the 2 hydrogens on now here, and I've already got that hydrogen attached. In order to make this carbon have 4 bonds, the only way I can do that is add another bond here. Now that got the hydrogens and that carbon correct. Now if I look at this one, this carbon has 1, 2, 3, 4. It's also correct. This one's not. I need 2 more bonds. And by the way, I should have put the lone pair on nitrogen first before I started doing any of this, because I don't want to forget it. Nitrogen has to have a lone pair. And so I need 2 more bonds to make this carbon work. And I need no other bonds to the nitrogen. It's got 3 bonds and a lone pair. So all of the atoms are correct. This is going to be the 3-dimensional structure for this molecule. Now, it's asking a question about this central atom. And I want the VSEPR. That gives me the number of atoms attached to this plus the number of lone pairs attached to this. So if I'm looking at that carbon right there, it's got 1, 2, 3 atoms attached to it. So it's AX3, and it has no lone pairs attached to it. So that's going to be the answer, AX3, and that's D on our exam question. So if you take a look, it is in fact D. All right, let's take a look at number 6 and see what that's about. It's the same molecule, and it's asking for the C-C-C bond angle. So number 6 is the C-C-C bond angle in the same molecule. Okay. All right, so let's go back and look at my pad. And now we can go back up here and look at it. It's asking for that angle, C-C-C bond angle, or C-C-C, it's the same either way you look at it. It's an AX3. What does AX3 look like? It's trigonoplanar. So I'm going to have a hydrogen. I guess maybe I can put the hydrogen here. I've got this carbon here, and this carbon here, and then the CN is up here. And the CCC bond angle is 120, or the HCC bond angle here is 120 as well, either way. So the bond angle is 120 degrees. And on your test question, that's answer A. Go back and take a look, and we can confirm that that's correct answer. And it is. It's a 120-degree bond angle. It's A. Let's look at number 7. Number 7. How many different molecules or isomers can exist for, I think I'll start a new page of paper. It says number of different molecules, 7. We call them isomers in this case. For the molecule is SCl3F3. Okay, let's switch back so that you can see my pad again. All right, so now sulfur's in group 6. There's 3 chlorines, and they're in group 7. And 3 more fluorines in group 7. That's 21 here and 21 here. That's 42 plus 6, that's going to be 48. And 48 divided by 8 is going to be 6. This is going to be an AX6. 6 molecule. And I have no lone pairs to put on. The octahedral shape for AX6 is like this. And so I'm going to put sulfur in the middle. Now, let's don't try to put all of these things on here at once. Let's just maybe pick the chlorine. And let's say, how many different ways could I put 3 chlorines on this structure? Okay, I could put one here and one here or here. That would be the same. So I could put one here, either one of these positions. So I can put 2 of the chlorines like that on 2 different axes like that. And the third one, I could put it, let's say, here. So if I did that, I'd have 1 chlorine on each of the 3 axes. So that's going to be one of the isomers. Fluorine is going to be in the other positions. Now let's do again and see if there's another way I can put the chlorines together. I can put the sulfur here. Let's go ahead and put the first chlorine here. I could put the other one on the same line with that one. And then the third one, I could put it right here, or here, or here, or here. All of those would be the same because they're all 90 degrees apart. Doesn't matter which one. So how many isomers can I draw another one? Well, suppose I tried to put the same 2 chlorines on this one. That's the same as this one here. Think about how you would describe them. In this one, all 3 chlorines, each chlorine is on a separate line, separate straight line. For the octahedrons, 3 straight lines. In this one, 2 of the chlorines on one of the lines and 1 chlorine on the other one. So you could waste a whole bunch of time trying to put all 6 of these atoms in every possible orientation you can think of, but there's actually only 2. And that's what we've got. One of the isomers has all 3 chlorines on each of the axes of the octahedron, X, Y, and Z. And one of them has 2 of the chlorines on one of the axes and 1 chlorine on one of the other axes. There's 2. So there's 2 possible resonance structures that you can get. And that's going to be answer B. Okay. Now let's look at SF3 minus 1. There's a question about this one. And this one's going to be a real easy one. 8 valence electrons in SF3 minus. Okay, so let's go back and look at the pad again. And now I've got to do the same thing. I've got to get my valence electrons. There's 6 for sulfur. It's in group 6. 3 fluorines are in group 7. And I've added 1 more electron because it's negatively charged. 21, 22, that's 28. So the correct answer is 28. And if you look at the problem, that's going to be answer D. So if we go back to look at our problem, as you can see, it is answer D. Now let's go down and do number 9. Now I'm going to warn you about this, and you look at the pattern. In order to keep you from having to do these same numerical calculations, same division over and over again, I'm using the same examples over and over again. I'll do that on the quiz as well, or the exam Monday, to save some time. But be very careful, because if I missed number 8 and I got a different number of valence electrons, I will automatically miss number 9. So be very careful when you're working these out. We can transfer the answers from one to the other one, but you have to be really, really careful about it. So number 9 is going to be the hybridization of the sulfur atom in the same molecule, SF3 minus. Okay, So let's get where you can see my pad again. Now, we've already created the structure up here. We've got 28 electrons, so let's do the division. 28 divided by 8, that's 3. 24 with remainder 4. Divide the remainder by 2, 4. Divided by 2 is 2. It's an AX3 E2. So I've got 5 pairs. So it's the hybridization we had a while ago. We've already calculated one like this. SPD, we need 1, 2, 3, 4, 5. So I use one S orbital, I use 3 P orbitals, and 1 D orbital. So it's sp3d is the correct answer for that. Or it could be written dsp3. So either one of these two would be correct. And so it doesn't matter how you put the D orbital either in the front or the back in terms of getting the answer correct. So let's go back and see what we've got on our practice problem for the answer. It's written as DSP3. And there's a story behind that, but right now I'm not going to bore you with it, and we'll just go on to the next problem. So we're going to do number 10. So let's pull it up, take a look at it, and then we'll work it out. Number 10. What is the molecular shape of SF3 minus? So number 10 is the molecular shape. I'm going to remind myself it said molecular, not electronic. Again, of the same molecule, SF3 minus. Now, let's go back and look at the pad. And I have this copied on my paper ready to go. And we've already created the shape earlier, or the hybridization. We said it was 5. We had sulfur on here. We had 2 lone pairs to put in. We put them in like that. And we'll have the fluorines on here and here and here. Now, I've not been putting the lone pairs on the other atoms, but you can do it if you want to. Right now, it doesn't matter for the question at hand, but you do understand you've got to have 8 electrons around all of these other atoms. And this middle atom is going to have 10 around it because it's not an octet rule structure. And this is a -1 ion. I could keep reminding myself of that. Okay, so what's the molecular shape? Again, leave off the lone pairs and look at where the atoms are located. There it is. It's a T-shaped molecule. And the T-shaped molecule answer is A. So let's go back and take a look. All right. And sure enough, the correct answer is A. Now let's move on to number 11. Now we're doing sigma and pi bonding. And so let's, the molecule is we want the number of sigma and pi bonds in O, C, C, H, C, N. Okay, now let's get where you can see my pad. And again, this is a structure like we did a while ago. We have to still use the rules. If I'm going to bond oxygen in an octet rule structure, it has to have 2 lone pairs and 2 bonds. So it could be like that, or it could be 2 lone pairs and a double bond for oxygen. So that's the only 2 way. Well, no, that's this. That's the only two ways oxygen is going to be bonded. Carbon has to have 4 bonds. And again, we saw all the permutations a while ago. 2 singles and a double, 2 doubles, a double and a single. And then, of course, hydrogen can only have 1 bond. And nitrogen has to have a lone pair and 3 bonds. And again, it could be 3 singles or a double and a single or triple. So let's see what we've got up here. The first thing we want to do is put our atoms down where they should go. Now that hydrogen can't be there because it can't have 2 bonds, can't be in between 2 atoms. It's got to be on that carbon. So I'm going to go ahead and put it on that carbon right now. And then the next carbon and the next is nitrogen. Now I'm going to put the lone pair required on nitrogen right now so I don't forget it. I'm going to put the lone pairs on oxygen so I don't forget them. Now I've got to get 8 electrons on oxygen. I've got to put 1 bond, one that's going to be called a sigma bond, so that everything is attached. Now actually I can go ahead and answer that question about sigma bonds because all I'm showing now are the sigma bonds. 1, 2, 3, 4, 5. So there's going to be 5 sigmas. Now I'm putting in pi bonds. I have to have another bond right here so that oxygen has this kind of structure. A double bond and 2 singles gives me an octet on oxygen. Oxygen is good to go. Now, to get this carbon correct, it has to have 4 bonds. I've got 2. I have to add 1 more bond to that one. Now, that one will be correct. This carbon needs 4 bonds, 1, 2, 3, 4. It has 4 bonds. This carbon needs 4. It only has 2. The only place I can put the other 2 are here. If I tried to put another bond over here, it'd give me 5 on that carbon. Would mess it up. So this one is correct. Nitrogen has to have a lone pair and 3 bonds, and it does. So this is the structure now that we get for this molecule. How many new bonds did I add? Well, I added that one and that one. That's 1, 2, 3, 4. So it's got 4 pi's. So 5 sigma and 4 pi's would be the answer. And that's A on your exam. Okay, so now let's go and look at number 12. Now, what is the hybridization of the middle atom in this molecule? Now, again, to save you time, I'm going to use the same example several places. So if I've screwed this one up here in number 11, I'm going to miss number 12 and 13 also. So always be careful when you see the same example used over and over again. You can use the results you've already done, but if you've missed it, it's going to be missed in the other examples too, probably. So what's the hybridization of the middle carbon atom? That one right there is the one we're talking about. So what I would do is, what is its VS EPR notation? How many atoms are there attached to that carbon? 1, 2, 3. So it's an AX3. Now, how many lone pairs are on that carbon atom? None. So this is the structure, AX3. All right, so now let's think about hybridization. I'm going to use S, P, and D orbitals. S orbital is one of them. There's 3 P orbitals and 5 D orbitals. S, P, D. I have to put in 3. 1, 2, 3. So this hybridization is going to be S1, P2. SP2 hybridization is going to be the correct answer. That'll be D on your practice exam on number 13 or 12. Okay, now let's go back over here and see what we got for number 13. We want the bond angle for that one. Well, that's going to be pretty easy for us to get. Okay, so let's go back and look at what we've done. We said AX3 is what we calculated up here. What is the shape of an AX3 molecule? Well, it's trigonoplanar. And so I'm going to have one of my carbon atoms here. I'm going to flip this over. I'll put one carbon here, one carbon here, one carbon here. I'm going to put that hydrogen up here. It's that one right there. So I'm going to put it up there where you can see it. Let's get this up where you can see it on your screen. Now, so we had AX3 from number 11. We said AX3 is going to be sp2 hybridization. And the shape is going to be like this. I'm going to have, but it wants to know this bond angle right here. Well, that bond angle is 120 degrees. So the correct answer should be 120, and that's B on your practice exam. All right, now let's, wait, I need to go back to screen share because I need to go get to the next problem. All right, so we're at number 13. We did say it was B, and that's correct. Okay, now, all right, now, we need number 14 instead of number 15. 14. Which of the following would dissociate into ions in water and be a strong electrolyte? You know, I think I can answer this for us right here. And let's just look at the things we have to consider. Well, maybe I better not. I'll go ahead and do it. A, B, C, and D. So the first one is AgCl. The second one is HClO4. The third one is H2S. And the fourth one is FeOH3. And we want to know, will separate into ions. Now, now let's go back and get it where you can see my pad, and then I can tell you as we go along. Now, there's two ways you can get separation into ions. One is soluble ionic compounds. The other is strong acid or strong base. So strong acids and strong bases will separate into ions, and soluble ionic compounds will separate into ions. This is an ionic compound. What does the solubility rules for ionic compound says? Number 1 says all chlorides are insoluble except silver, mercury 1, and lead. So silver is not a soluble chloride. So it's an insoluble chloride. So this one will not separate into ions. It's just going to stay as the solid. HClO4, this is a clue, it's an acid. H is in front, at least with this kind of structure. And you might even recognize that. This is perchloric acid. You should recognize it. And it is a strong acid. Okay, so that answer would work. Let's see that the others don't. So this one doesn't. Now, H2S, that's hydrosulfuric acid. It's not one of the 6 strong acids we memorized. HCl, HBr, HI, H2SO4, HNO3, and HClO4 are the strong acids. Every other one is a weak acid. So this one will not separate into ions. Now this is an ionic hydroxide. What are the solubility rules for hydroxides? All hydroxides are insoluble except group 1 and group 2. Well, iron is not a group 2 hydroxide, so this will not separate. It will remain as a solid. It's an insoluble hydroxide. So the correct answer is B. Now let's go back and look at the question again. And let's look at number 15. Okay. All right. Now this is an activity series, and I do recall rewriting this question for your exam. There's a problem that I've run into with putting exams on quizzes in D2L. I've not found yet how to attach a file to a quiz. I know how to upload files, do all that kind of stuff, but I have not found a way to, for example, link this question 15 to a activity series. So this one we would have to answer using a activity series table. I rewrote it so that I could put a portion of the activity series table directly in the question. So you won't have to hunt all over everywhere to find the species that are in your reaction and just determine whether the reaction will take place or not. So I'm going to copy this down, and I think down at the bottom we are going to have an activity series. So maybe I'll go down there to answer this question. The first one is 2Ag reacting with copper, Cl2. I'm not going to write the products right now. All it is a single exchange reaction. Silver going in, copper coming out. That's A. For B, we've got, I'm going to write it 2Ag plus 2HCl. I just changed the order to make it easier for us to use the table. Is going to product. And again, what's going to happen is silver going in, hydrogen coming out. Let's see if that would happen. C is copper reacting with 2HCl to form copper chloride plus hydrogen gas. But the important thing, can copper push hydrogen out? And then the D is iron plus 6HCl going to, it's going to be iron chloride and H2 gas coming out. So let's see which of these could possibly happen. Now, I didn't show you what I had. So this is what I've got. I want silver pushing copper out, silver pushing hydrogen out, copper pushing hydrogen out, or iron pushing hydrogen out. And now let's go over here and see if I can get the activity series over here off the ends of this exam. I'm hoping it's down there. There it is, right there. Okay, so let's look. Does silver displace copper? So silver is right there, copper's up there. So no, that reaction would not occur. So I can X out A in my answers. The B answer was silver and hydrogen. Well, no, it's not going to happen. Silver's down here and hydrogen is above it. So B is not going to happen either. Copper, can it push hydrogen out? Nope. Copper's below hydrogen. So C is wrong. The answer now left is iron. Can iron push hydrogen out? Yes, it can. Iron is above hydrogen. So the correct answer to this one is D. And we go back up here and get back to where we were, 15. Okay, so the correct answer is D. That reaction will occur. Okay, let's look at number 16 and see what we've got. We've got, assuming the reaction takes place in water, which of the reactions below represents the net ionic equation corresponding to this molecular equation? So I've got number 16, the molecular equation is 6HNO2 and Al2S3 goes to 2Al NO2 3 and 3H2S. Okay, so let's switch back so you can see my pad again. All right, so here's the pad. This is the reaction right here that we're going to try to write the net ionic equation for. So I've got to know what separates. HNO2 is a weak acid. It does not separate. So I'm going to write 6HNO2 aqueous is what it's going to be. Now, let's add to this. Al2S3, will that separate? Well, it's an ionic compound, and sulfides are all insoluble except group 1 and ammonium, so from the solubility rules. So this one will not separate either. It's insoluble ionic compound, so it's going to be Al2S3, and it's going to be a solid. Now, do we separate the aluminum nitrite? Yes, all nitrates, acetates, and perchlorates are soluble. So aluminum nitrite is soluble, which means we're going to pull out 2 Al3 plus and 3 NO2 minus is going to separate like that. So I'm going to get it separated. And now H2S, it's an acid, but it's a weak acid. It doesn't separate. 3H2S. Now, this would be the ionic equation. To get the net ionic equation, we cancel out anything that appears on both sides. So the net ionic equation is the same. There's nothing to cancel out. And nothing on this side that we can cancel from this side. So it's the same one. Now, that would be answer A on your quiz question. So if we go back so you can see the question and see the answer, you can see we did not separate the HNO2s. We did not separate this because it's an insoluble sulfide. We did separate the ions of aluminum nitrite because the nitrites are soluble, and we did not separate the H2S. So the correct answer for this one is, in fact, A. All right, so and we keep going. All right, so number 17. What is the oxidation number of uranium in zinc uranyl acetate? So it's zinc, UO2, C2, H3, O2, and there's 4 of those in this compound, zinc uranyl acetate. By the way, all of the sodium salts are soluble except the sodium salt of this compound. If you had sodium Na2 uranyl acetate, it forms nice, beautiful crystals. You know, we used to do that experiment in lab, and uranium is radioactive. It's an alpha emitter, so it's not terribly dangerous to us, but we wouldn't dare do that reaction now. But when I was in chemistry lab, we actually did that experiment using zinc uranyl acetate. And that stuff is so beautiful. It's a really lemon yellow color, just almost fluorescent lemon yellow. It's a beautiful compound. Okay, but aside from that, I wanted to separate out some things like cations and anions. Zinc is coming first, and that's a metal. So that's a cation, and I know zinc is +2. All right, now this is an acetate ion, and it's -1. So right over here on this side, I've got 4 of them, so this is -4. Now, what do I have to have in the middle so that the total charge is 0? I have to have a +2. So the zinc is +2, UO2 is +2, and these 4 acetate ions are total -4 in order for the charge. Now let's look at the uranium and see what its charge has to be. UO2, and it's going to be a +2. Now let's separate it the same way. Oxygen is always -2. So -2 times 4 gives -4. So what do I need to take away? What do I need to have uranium to be so that the result is going to be a +2? Well, I think it needs to be +6, doesn't it? Look, +6 -4 is +2. So uranium is +6 in this compound. That is A on your exam answer. So if we go back over here, whoops, I already had it up there, didn't I? I didn't show you my paper. Well, now I'm showing you my paper. There's the way I divide it up. Zinc is +2. Acetate is -1. There's 4 of them. That gives me -4. So this part right here, the UO2 has to be +2. So UO2 is +2. Uranium, oxygen's always -2. So there's 2 of them. That's -4. So the uranium has to be +6. So that +6 -4 gives you +2. So that's what we were going with a while ago. And the answer then is the uranium atom is +6. All right, and now we're going to do number 18. Now, 18, and we've got the reaction is 3P4 plus 20 HNO3 plus 8 waters is going to make 12 H3PO4 plus 20 NOs. Okay, I've got the information copied to my screen, so on my pad, so I'll make it visible to you. No, I already did, didn't I? Stop the screen share, go back again. Already had it on there. So I copied it off of the question though for you. The question was, which species is oxidized and which one is reduced? Well, this is an element. So I know phosphorus in this compound is 0 because the oxidation state of all elements not in compounds is 0. Now, if I look at phosphorus over here, let's see what phosphorus is over here. Well, the oxygens are -2. So 4 of them, that would be -8. And the hydrogens are all +1. And there's 3 of them. So this is +3. So +3, I got -8. This has to be +5. Because +5 +3 is +8 with 4 oxygens -8. So phosphorus has to be +5. So phosphorus goes from 0 to +5. That's oxidation. So phosphorus is oxidized. So right now I can eliminate C and D. It couldn't be C or D because they are responses that have phosphorus reduced. Now let's look at nitrogen. Nitrogen is in this compound right here. And let's see, what does its charge have to be? Well, Oxygen, 3 oxygens is -2 each, so this is -6. Hydrogen is +1. So nitrogen has to be +5 in this compound. So for nitrogen, it goes from +5 to something over there. What is it over here? There's the nitrogens. Oxygen is -2. That means nitrogen has to be +2. So nitrogen goes from +5 to +2. That's reduction. So that means that this species, HNO3, is reduced, and phosphorus, P4, is oxidized. Okay, so there's my correct answer. And B, that would be B on your exam. So if I let you see it again, you'll see the answer on this one. There it is. Phosphorus is oxidized and nitric acid is reduced. That's the correct answer. Let's look at number 19. Okay, number 19. Number 19 is, what is the molecular formula of a compound at 62.78% mercury, 17.17% manganese, and 20.03% oxygen? The molar mass is 639.06. Okay, you know what? I'm going to show you the quick and dirty answer to get to this one. And then I'm going to show you the long, well, no, let's do the long way first, and then I'll show you the short way. So let me write down the data. It's 62.78% mercury. It is 17.19% manganese, and it's 20.03% oxygen. All right, I've got the data copied across, and the molecular weight, I'll write it down too. Molecular weight is 639.06. Okay, now let me get it where you can see my pad again. So here's my pad with the data that I need. 62.78% mercury, 17.19% manganese, and 20.03% oxygen. Molecular weight, 639. Now, the way I'm going to do it is the way I showed you in class. I'm going to get the compound is HGX MNYOZ. And my job is to determine what X, Y, and Z are in the formula of the compound. Now, what we're going to do is, if I wanted the percent of mercury, what would I do? I would take the mass of mercury in the compound. The mass of mercury, there's X of those atoms, and the atomic weight of mercury is, this is Mn up here, I see, I screwed up. The Hg is right there. It's 200.59. Now that's the moles of mercury in a formula weight of the compound. So I'm going to divide by molecular weight, multiply by 100. That gives me the percent, but this percentage I already know. It's 62.78. Now let's do the same thing for the percent of manganese. Well, it's the number of manganese atoms. That's why the molecular atomic weight of manganese, located on the periodic table right here. Molecular weight is 54.94. I want to divide by molecular weight and multiply by 100. And this value is given in the problem at 17.19%. Now, if I divide these things out, then molecular weight cancels, the 100s cancel. What I've got is 200.59 times x divided by 59.94 y is equal to 62.78 divided by 17.19. I'll go ahead and cross multiply. 17.19 times 200.59 times x will equal to 62.78 times 59.94 times y. Now let's do all the math here and put the numbers down and make it look a little better. 17.19 times 200.59 equals. So this is 3448.1 and some other digits times x has to equal 62.78 times times 59.94 times 59.94. Is that right? That's 54.94. Yes, that's 54. That's the molecular weight of manganese. It's 54. I copied my number wrong. So that's 54. So let me back that up and get the right number in here. 54.94. And that's going to be 3,449.1 y. If you divide that out, essentially you got 1x equals 1y to the nearest whole number. So that means x is 1 and y is also 1. I'll get another piece of paper here. We can continue this one. Okay, so now I've got two parts of the formula. The compound is HgMnO, and I don't know what the Z is. So I've got to solve for the number of oxygens in the formula of the compound. So if I ratio the percent of mercury to the percent of oxygen, what I've got is 1 mercury, and the atomic weight of mercury is 200.59. And the number of oxygens, I have Z for that, and the atomic weight of oxygen is 16.00. Now that's going to give me my percent of mercury in the problem. It was 62.78. And the percent of oxygen is 20.03. Now, I'm going to cross multiply, so I get 1 times 200.59 times 20.03 has to equal to 16.00 times 62.78 times Z. Now all I got to do is solve for Z. So I'm going to multiply these together and divide by that. Let's see what we get. So we take 200.59 times 20.03 divided by 16 and divided by 62.78. And I get, wow, 4.75. Now here I want to be a little bit careful. I may have made a mistake here. This number doesn't look good to me. But let's see what we get. That's 4.75, and that's 4 plus 3/4. This is going to be really, really big. So I'm thinking this is not right, but never mind. 4 would be 16/4. Now this is not going to work off. This would need to be an 8, I guess, to round off. But I've got a question about this. We'll take it up in just a second. It should have been closer than that. Let me double check and see if my math is okay. I need to see this screen just a little bit better. Okay, now, and all right, and let's see, I had 200.59, that is the correct weight for mercury, I think. Hg is right there, 200.59, so that is the correct molecular weight. The percentage of oxygen was 20.03, that is correct. The molecular weight of oxygen was 16, and that's what's, maybe I did the cross multiplication wrong. Let's see, 16 times 60, no, that's right. Mercury is 62.78, oxygen is 20.03, that's correct. So this would be 200.59 times 1 times 20.03 is 62.78, that's correct, times Z times 16. Let me do this math over again and see what I get. 200.59 times 20.03. This left-hand side is 4017.8177 is equal to, now, 16 times 62.78 is that, 1004.48 Z. Yeah, I made a math error a while ago. So if I take 4017.8177 and divide by that answer that I have, it's 3.99999. So Z is going to be equal to 4. So my formula that I would predict from this would be HgMnO4. Now, that might be right, but I don't know that it is because I've got to check for molecular weight. The molecular weight is 639.06 for this molecule. Now, if I add up this molecular weight, I have 200 point, what did I say? 59. Manganese is 54.94. And 4 times 16 for the oxygen. Let's see what we get for molecular weight. It's 200.59 plus 54.94 plus 4 times 16 is 3319.53. So this doesn't have the correct molecular weight. This is looks like it's twice that. So if I multiply that by 2, yes, it does come out 239.06. So that means that the correct formula is Hg2Mn2O8. And the correct answer then is going to be Hg2MnO4 2. So that's the correct formula for that compound. Now, here's what I was going to tell you. The quick and dirty way to get this one is a lot of work to get to here. But if I looked at this and said, hey, give me the molecular weight, which one of these has the correct molecular weight? It'll be that one right there. So to get this problem, if they give you the molecular weight, all you got to do is just add up molecular weight of the answers, and the one that has the correct molecular weight is the correct answer. How about that? Okay, so that'll be much easier doing it that way. But you do need to know the other way in case they didn't give you the molecular weight. You could still get the empirical formula. But notice the empirical formula was a wrong answer here. There's the empirical formula that you get from percentages, but there's the correct molecular formula. And you should recognize that as a real compound or a real possible compound. Mercury 1 permanganate would have that formula. What's the molar mass? This one now is the molar mass, and we're doing number 20 now. And we want the molecular weight, molar mass of UO2, 3, PO4, 2. Well, that's going to be real easy, but I'll pull it over so you can see my scratch pad again. Okay, well, we've got 3 uraniums, and from this part, we've got 6 oxygens. From this part, we've got 2 phosphoruses, and we've got 8 oxygens. So we've got 3 uraniums, 2 phosphoruses, and 14 oxygens in the compound. So the molecular weight is going to be 3 times uranium is 238.03 from the periodic chart right here. Uranium 238.03. We've got to add 2 phosphoruses. Phosphorus is right here, 30.97. Plus we've got 8 oxygens. Atomic weight of oxygen is 16. And now let's see what we get for molecular weight. So it's 3 times 238.03 plus 2 times 30.97 plus 8 times 16. I get 904.03. And 3 uraniums, 6 oxygens, 2 phosphoruses, 8 oxygens, 6 and 8 is 14. So 3 uraniums, uranium is 238. Uranium is 238.03. Phosphorus is 30.97, that's correct. Oxygen I know is 16. Let's try one more time. 3 times 238.03 plus 2 times 30.97 plus 8 times 16. Well, I think there's a mistake on this problem. I did copy it correct. UO2, 3, PO4, 2. That is what's in the problem. I'm getting 904.03 twice. The problem says the answer is 999.93. So it says that's the correct answer, but I think it's not. So after we're done with this, I will upload a corrected number 20 to D2L. I'll work it again before I do that just to be sure I haven't made a mistake this time instead of last time, okay? All right, so let's go back to screen share so we can see the next problem. Okay. I'm surprised I didn't catch that sooner. Okay. 21. How many grams of nitrogen? Grams of nitrogen in 23.5 grams of the compound is NH4 C2O4. Molecular weight is 124.1. Okay, I've got the problem copied across. Now let's stop screen share so we can see the pad again. All right, so here's the data. Now what we're going to do, we want grams of nitrogen in this compound. So I've got 23.5 grams of compound. And I'm just going to abbreviate all that CMPD because I don't want to write out that whole formula again. I want to do a conversion factor. I want to go from grams of that compound, and I want to go to grams of nitrogen in the compound. Now the question is, do I know a mass of that compound for which I would know how much nitrogen and oxygen and carbon is in it? Yes, I do. 124.1 grams. That's a mole of the compound. It's going to have 2 moles of nitrogen. That's what we're interested in. So it's 2, the molecular weight of nitrogen is 14 from the formula. So if I divide that out, that ought to give me my answer. So it's 23.5 times 2 times 14.01 divided by 124.1. So I get 5.31 grams of nitrogen. That would be in 23.5 grams of this compound. If we go back and look at our answers, that's B. So that is correct. 23. Here is a reaction. It's 22. I said 23. It's 22. Number 22. And we've got, let's see what we get. 22. We've got a reaction. What mass of nitrogen dioxide can form by the reaction of 3.5 moles of perchloric acid? So here's the reaction. 8CH3 NH2 reacts with 13 HClO4s to make 8 NO2 and 8 CO2s and 20 H2Os and 13 HCl's. Now let's see what's involved in the problem. It said what mass of nitrogen dioxide, so how many grams of nitrogen dioxide will form by reacting 3.5 moles. Okay, now I'm going to switch over so you can see my pad again. And so I've got the problem set up. This is the balanced equation. I'm only dealing with this compound and this one. So I don't care what's going on with the rest of them. But now the equation is showing, it wants me to have 3.5 moles. The balanced equation has 13 moles. I want to know how many grams of this compound. The equation is showing 8 moles. And the molecular weight given in the on the test sheet was 46.01 grams. So this is how many grams that you would get if you reacted these together. Okay, there is my rebalancing factor. The RBF for this is 3.5 divided by 13. The answer is the RBF, rebalancing factor, times what we've got here under this question mark. It's 8 times 46.01. So my answer is going to be the RBF is 3.5 divided by 13 multiplied by 8 times 46.01. And that'll be grams of the NO2. All right, so let's do the math. If I take 3.5 and divide by 13, that would give me that number, but I don't need it right now. I just multiply it by 8 and multiply it by 46.01. And my answer comes out to be 99.1 grams of the NO2 is what we would form. So let's go back and look at our answer on the test. And the answer on the test is C. So that's going to do C for the problem. And let's go back, go down and do number 23. Oops. Now, this is number 23. And get a new piece of paper, number 23. The problem says, same equation that we had a while ago, but says what mass of water will be formed by the reaction of 3.5 grams of methylamine. So the methylamine, there's 8 of those, CH3, NH2, and we've got 3.5 grams of that. And the molecular weight is, the amount shown in the balanced equation is 8 moles, and the mass is 31.06. So that's how much methylamine. And 15 grams of the perchloric acid. The perchloric acid is 13 HClO4. And we have 15 grams of it. The equation is showing 13 times the molar mass of perchloric acid is 100.5. And we want to know what mass of water. So it's going to go to 20 H2Os, and I want to know how many grams. The equation is showing 20 times the atomic weight is 18.02. Okay, now I've got this set up. Let's go over so you can see my pad to see where I'm going. So here are the two things reacting in the problem. 8 CH3NH2s, 13 HClO4s. The problem amount had 3.5 grams of this and 15 grams of that. The amount shown of this in this equation is 8 moles. Its molecular weight is 31.06. This one we wanted 15 grams. It's showing 13 grams. The molecular weight of HClO4 given in the problem was 100.5. We want to know how much of this we form. In grams, the equation is 20 moles. The molecular weight of water is 18.02. So I've got two rebalancing factors, one here and one here. So my two rebalancing factors, I'm going to do the first one first and see what we get. We take 3.5 and divide it by 8 and divide it by 31.06. So I'll take 3.5 and divide it by and divided by 31.06. My first rebalancing factor is 0.01408. I don't need that many significant figures, but I'm just going to leave them there. 15 divided by 13 and divided by 100.5. That's 0.01148. Now, if I compare this to, this is smaller. So this is my limiting reagent. So that's going to determine how much of everything else is used. So if I want to get the answer, that's going to be the rebalancing factor here, 0.01148, multiplied by what we've got under my question mark is the number of grams of water is 20 times 18.02 times 20 times 18.02. Now, just by luck, I calculated this one last, so it's still in my calculator. So I can finish this calculation just by saying times 20 and times 18.02. And I get 4.1377 is 4.14 grams of water. And I think that's response B. Let's go over here and see. So I can go back to screen share so you can see the exam again. Yep, there it is, 4.14. Now number 24. Number 24 is which of the following name combinations is correct? Now I don't really need my pad for that. Let's just see if these names are correct. Well, Al, aluminum with carbonate, that's carbonate. Aluminum is one of the ions that doesn't require Roman numeral. Remember, they're group 1 and group 2, and zinc, cadmium, aluminum, and silver. Aluminum does not require Roman numeral. It doesn't need a Roman numeral, so it could be aluminum something. But CO3 minus 2 would be the charge for this because aluminum is always plus 3. And CO3 minus 2 is called carbonate. So which one is incorrect? Hey, I hit it right on the first one. But let's explain why the other one isn't correct. What is correct? Well, tin is combined with oxygen. Tin does require a Roman numeral. Oxygen is always minus 2. That makes this tin a plus 2. So it is tin 2 oxide. This is iron, and this is hydroxide ion, so that's correct. There's 3 of them. Hydroxide is minus 1. So with that minus 1 times 3, the iron has to be plus 3. So it is iron 3 hydroxide. Now, lithium and aluminum are both metals. Hydrogen is in the anion position. So hydrogen as an anion would be called a hydride. And you just name the metals. It's lithium, aluminum, hydride. Now, is the formula correct? Lithium is always plus 1. Aluminum is always plus 3. Plus 3 plus 1 is plus 4. I need minus 4. Each hydride ion, hydrogen is always minus 1 as a hydride. That is the correct name and the correct formula. All right, so let's go down to number 25. Nomenclature we can do again without the pad. If I'm looking at this compound, it's nickel combined with something. So it's going to be a nickel something compound, and the nickel is going to need a Roman numeral. We would never name a compound like that involving a metal like this. It can't be trinickel diphosphite. Although that is phosphite, and although that is 3 nickels, we never ever use the the prefix is like that, except in nonmetal compounds. Never when it's got a metal in it. All right, so it is phosphite. You should have memorized phosphite is -3. So -3 times 2 would be -6. 3 nickels has to be +6. Each nickel is +2. So this compound is nickel 2 phosphite. That is the correct answer. What is the name of this compound? Well, it is an oxyacid, and it's going to be named from the polyatomic anion. Well, ClO2 is ClO2 minus 1 is chlorite. So this is going to be chlorous acid. It's going to be this one. It's not chloric acid. That would come from chlorate ion, ClO3. It's not hydrochloric chlorous acid. There is no such thing as hydrochlorous acid. There's a hydrochloric acid, but there is no hydrochlorous acid. And it can't be dioxygen, hydrogen, or hydrochloric acid. That just, I made that up. It's nothing at all about that that's any good. Now, number 27. So for number 27, we're going to go for chromate. Chromate is CrO4 2 minus. And we want the charge of that compound. So CrO4 2 minus is -2. So that's the correct answer for that. Those last three were nomenclature. They're very, very easy. There's 3 more exam questions that are just general information questions. So 28, 29, and 30 will be surprises, but they won't be a surprise. So everything should be okay. So this completes the entire practice exam. I hope you find good use of this. And if you have any questions, I'll try to hold some kind of a morning, maybe office hour on Monday, or at least sometime during the day for your class, for those who are available. I would appreciate you dealing only with checkpoints and checkpoint questions on that one, or anything that's not clear that I've done today. That'll be okay. Okay, so we are finished with this, and I'm going to end the meeting now, and I will upload this video as soon as it converts to D2L. You should have it later on tonight and for all day, Saturday, Sunday, and Monday. Well, anytime you want it. It should always be there. Okay? Have a good weekend. May God keep you safe and keep that virus away from you and everybody you know.